today's lecture, where we are going to introduce fundamental domains. Yeah, like this class of locally finite fundamental domains. Which kind of introducing them somehow in the very, in a way, is fundamental domains in the end can provide us with some sort of reverse engineering that allows us to produce Fuchsian groups. Somehow that's somehow in the long run the idea. And also one can visualize. It also helps to visualize kind of the geometry of U modulo gamma, modulo the action of a Fuchsian group gamma. Yeah. So just kind of to agree on some terminology. If I have the action of a group on a set X, a fundamental set for the action is a subset that contains exactly one element from each orbit. Right? And now, now one point is that even if kind of X has some geometric structure, and even when G acts respecting that geometric structure, let's say that X is a topological space, say, and even if when G acts by homeomorphisms, a fundamental set is kind of, this definition is just a set theoretical definition, right? So somehow this doesn't recover any geometry of the set, if any. The notion of fundamental domain attempts to take the geometry into account. So recall that also that a subset of the complex plane is a domain when it's open and connected. Right, and then if I have a Fuchsian group, I call a subset of the hyperbolic plane a fundamental domain for gamma if it is a domain, so open and connected. And here somehow, well, okay, I will say some words about why I'm using the letter H, right? So somehow the point is that I start using the letter H just kind of for hyperbolic plane in order kind of to tacitly state that what I'm about to say is valid regardless of, say, whether I take this model of the hyperbolic plane, namely U, or this model, namely the Poincaré disk. Right. So somehow that's my intention when using the letter H. So somehow that the concepts make sense. Kind of they make sense not only for one model, but at least for those two. Yeah. Okay. So a fundamental domain is for gamma is a domain with the property that in between that domain and its closure, its topological closure in the hyperbolic plane, in between there is some fundamental set. So in between. And its hyperbolic area, I require it to be, sorry, not its hyperbolic area, I require the hyperbolic area of its boundary to be 0, the boundary. So just so for instance, notice because of this definition, since in between D and its topological closure in H, there has to be a fundamental set, different points in D are not in the same orbit, right? Are not in the same gamma orbit, because here in F, different points really are in different orbits, right? So so different points are not gamma congruent. So that's something that can be deduced from B. And then as examples, let's say that I have this Fuchsian group, which yeah. So okay. So here you see it's the Fuchsian group consists of multiplication by 2. Although you see the matrix here, I'm not taking it. It was not in SL2R, right? But the transformation itself is in PSL2R. And then if I take, yeah, so I have here the real axis. So and somehow what I'm and then it's multiplication by 2, and what I'm doing here is I'm taking just this somehow annulus. So this is 0, and then oops, well, more or less. Yeah. So somehow it is more or less easy to see that this region is a fundamental domain for this group, multiplication by 2. And then a non-example. So for that same gamma, now let me draw another. So again, here what I take is real part between 1 and 2. So somehow here is 0, let's say 1, and let's say 2. Yeah, and you see this region satisfies to be a domain, satisfies this. It also satisfies that if you give me 2 points here in this D2, two distinct points, they are not in the same gamma orbit. However, D2 is not a fundamental domain, right? Because somehow with this, it is impossible to obtain the negative quadrant.
One of those strict inequalities should be inequality, right?
That should be an equality. Not quite, right? Because
not equality, but like a smaller equality.
Right. Yeah, like a non-strict. Let's say here.
Yeah, on the left hand side.
What do you mean here?
The first, yeah, that example.
No, because domain is open and connected. So you see the fundamental set, it's in between, but I don't claim it to be either, or yeah.
I see. The open thing is called fundamental domain.
The open thing is the fundamental domain. Yeah. And then fundamental set. Okay. Yeah. But so a fundamental set would be, let's say, the open domain union. Let's say this. Yeah, union that segment. Then that would be a fundamental set. Yeah. Or union the other one, right?
Yeah.
Or even like union something like this. Right? Yeah, and then from here, the point is that, for instance, the point negative, I don't know, something, whatever here in the negative quadrant can never be put here via multiplication powers of 2, right? Which is the subgroup generated by multiplying by 2. So example and non-example. Right. Yeah. So yeah. Okay. Yeah. But something that must happen in particular is that since a fundamental set has to be in between, every point in H must be gamma congruent with something at least inside the bar. At least in that topological closure, which, by the way, it's the topological closure in H. So let's say in the model U, this D bar, this topological closure is taken in U, not in U bar. Right. So this one may fail to be closed in C, let's say, or in C bar. Right. Now, some exercise, which kind of looks long, but it's really not so much. I mean, it's actually a little bit redundant. So, for instance, here it's something that I already mentioned, that different points in D are never gamma congruent. So different points are never in the same gamma orbit. And then let's say three that if you give me a point in D and a non-identity element, then this actually takes it completely out. So gamma takes the point in D completely out, not only of D, that we already know, because otherwise they would be in the same gamma orbit, but not only out from D, but actually out from the topological closure. And this is actually not so hard. So let me show you what happens. So let's say that I have somehow D there, and I have Z, and then I know that if I take gamma different from the identity, gamma of Z is not in D, but let's say that it's in D bar. So it would be like really in the boundary. But you see, D is open, so there is some disk around it, completely containing D, and then its image under gamma would be, of course, again some hyperbolic disk, and this hyperbolic disk would contain both points from D and points from outside D, but then there would be some points in D, right, which would necessarily be different if I take this one to be sufficiently small so as not to intersect this other disk, right? And of course, there I'm using that Z is not elliptic, right? So so one would have to argue why it's not elliptic. Well, if it were elliptic, you see there would be like some point here which would be gamma congruent with some other point in the same disk, in contradiction with the disk being contained completely in D, right? So such Z is not cannot be elliptic, yeah. And then taking this disk completely contained in D sufficiently small so as to not to intersect the image under gamma, you would have here points in this disk, which are in the, you see, kind of, they would be different points in D in the same gamma orbit. Contradiction with one, right? So for instance, I pretty much argue with 3 for U, and then if you think about it a little bit, in this when you read the exercise, 3 and 2 are closely related, right? I mean, if I have 2 points and are in D bar and they are gamma congruent, then it cannot be that one of them is in D, because then I apply the argument I just gave. Okay, and then similarly, well, you see, for instance, 5. If I have 2 different elements, then this intersection has to be empty, because otherwise I would have, you see, gamma 2 inverse gamma 1 of D would intersect D, right? And then I would have I would have that either, if this is different from the identity, I would have different points in the same orbit, right? So this would have to be the identity, but then they have to be equal. Okay, so this exercise is really not so hard. Something that can be said more or less immediately, and here I should have used the letter D instead of F, is that if I have two fundamental, I should have said, should I have said domains? No, okay, no, probably sets is okay. Okay, we will see. Whose hyperbolic areas exist, then they have the same hyperbolic area. right? Which kind of goes in the direction of defining the hyperbolic area of H or U, if you want, modulo gamma. Okay? And that hyperbolic area somehow should equal such hyperbolic area. So let's go more or less quickly with the proof. Oops. So the area of one of them is, you see, F1 is how to say, you see, with F2 and all its gamma translates, I cover the whole hyperbolic plane. So F1 can be expressed by simply the part of F1 that lies in those gamma translates. Okay, so this is just the equality between whatever is inside, and then the distribution, right? So F1 intersect a union is just the union of the intersections. Okay, so somehow the Morgan laws. Right, and then here these are all the sets that appear here. They are all pairwise disjoint because F2 is a fundamental set, so they are all pairwise disjoint. So when I take the hyperbolic area, it's just the sum. There I have a little hiccup that is that sometimes I think that to actually be sure of this, one needs Lebesgue integral and not Riemann integral. But okay, but now if one can separate if one can compute the area of this union as just the sum of the areas. From here to here, one uses that the area is invariant on their elements of PSL2R, right? Under the isometries that preserve the orientation, and actually under all isometries. And then once one can say, okay, and then you see somehow the point is that from here, from this of F1, I could say that the area of F1 could be written as this sum, right? Where the sum is over all elements of the group, and its area of F1 intersection the translate of F2, right? And notice that here it's really the sum over all elements of gamma, right? And then its area of F2 translate of F1, and here is kind of just a small change of variable. So if I applied all this all this to F2 now, I would really arrive at this one. So this one is the area of F2. Or if you want, I can just kind of rebuild the path back to the area of F2. And then they are equal, yeah, except for this this area of this you see this joint union, that it really gives me the sum of them. And for this kind of looks to me clearer if we just use Lebesgue integral. By the way, yeah, perhaps before I go into locally finite fundamental domains, by the way, here this is a countable sum. In other words, gamma, a Fuchsian group, is always countable. So let me try to argue. Let me see if I can produce an argument for this theorem. So let's see. Um, yeah, it's either finite or countable. Yeah, so it's just, I will just say it's countable. So it's we want is not uncountable. So let's see. Uh, let's see. I used to know an argument. Now I'm hesitating. Um,
Maybe it's finitely generated.
they could be infinitely generated.
Could be
Yeah, yeah, that could be. What I would say is more that let's say in Rn, which in Rn, a subset which does not accumulate is at most countable. I think that's the, so somehow it's more general to the topology of Rn, and then here you know you would take the inverse, pi inverse of gamma in SL2R, right? So the corresponding pre-image of gamma in SL2R, and SL2R is in R2 times 2, right, which is R4. Yeah, so I think it's kind of the following. I think I'm going to produce just kind of an argument in R2, but I think it's valid in R4. So in R2, take the integral lattice, so the points with integral entries. Right. Yeah, and around each of them, consider the square centered at the point. You see of sides of length 2. Right? So around each of them. And it's kind of just the closed square. So it's compact. So it's compact, and you know that you have something that doesn't accumulate at all. So the intersection with each of these squares is finite, and the union of all these squares covers everything, and there are countably many squares. So it's the union. Even the squares, they overlap, but I don't care. But it's a countable union of finite sets, and so it's countable, right? And this argument can be applied in for in R2 times 2. Okay? You just take the corresponding cube of sides of length 2. Yeah. So the point is that the point is that Rn can be covered by countably many compact sets. Yeah, so that's the point. Okay, yeah. So this is countable. So okay, so this was kind of just the observation that this sum is really just a countable sum, and that here this is really a countable union. Countably many sets. Okay. And now we're going to enter these locally finite fundamental domains, which we are going to see that they have certain nice property. Because you see, one takes, let's think about just the, well, here in again here in R2. R2. Well, okay, that doesn't look orthogonal at all, but in R2, and then modulo the action of Z squared, right? So the one that we saw before, kind of when we tried to motivate studying seeing that there is a natural Riemann surface structure on the torus. Right, and then one has R2, or if you want C modulo Z square, which one can also write like this, right? And then this is kind of how does one form this? Well, one really has to take all of this and somehow start like wrapping the plane around itself, right? Like for instance, if one consider instead of Z square just the translations, just horizontal integral translations, then to form the corresponding quotient, so integral translation. So this would be just Z, integral horizontal translations. Then somehow to visualize this, a priori is kind of one has to take this, and then start to wrap around, right? To wrap around, and somehow the picture would look something like that, right? Etc. Right, but then of course, and then coming back here to Z square, one realizes that what one learns very quickly is that you actually all you need is somehow is to consider this square, the unit square, and say glue the corresponding opposite sides, right? And then you are still visualizing this, right? So so really what is doing is one is using the this fundamental domain to try to obtain a visual picture of the corresponding quotient more easily, right? Kind of by just gluing sides of a fundamental domain. And so somehow that's the question here. So suppose now, but I mean now of course I'm not working with R2 or with the complex numbers. I'm working now with the hyperbolic plane, and instead of Z square, I'm working with a Fuchsian group. And of course I can you see, kind of I'm interested in visualizing this this space, but I can also take just the fundamental domain and then somehow do the gluings that the group kind of orders me, right? Somehow like here these gluings somehow they really are the gluings that the subgroup orders, like dictates. Right? And of course, I know that d bar is not closed under the whole action of gamma. This I know, right? But but still, I can still say, okay, so in d bar, identify points whenever they belong to the same gamma orbit, and then I have this obvious continuous map, which is actually I would say is actually bijective. So I would say that this is always bijective, and that is not hard to prove. And the question is, when is it a homeomorphism, right? Being able to answer when it is a homeomorphism, or let's say if I have a fundamental domain for which this is a homeomorphism, what I would be saying is precisely that the fundamental domain would be allowing me to visualize this simply in terms of performing the gluings that the group gamma dictates. The answer for when it is a homeomorphism is actually going to be precisely when the fundamental domain is locally finite. Right? So a locally finite fundamental domain for my Fuchsian group gamma is a fundamental domain, of course, with the property that for every compact subset of the hyperbolic plane, then the number of elements of gamma that transport part of d bar inside the compact set is finite. Right? So that only finitely many gammas can take d bar close or inside, no, not inside, but kind of can make it overlap with k. Only finitely many gammas, and this for any given compact set. Right? So that's the definition of being a locally finite fundamental domain. And what we are going to see somehow, I would say, maybe the main theorem of today is going to be that the answer to this question is that this iota bar is a homeomorphism precisely when D is a locally finite fundamental domain. Right, and then of course, then the question is going to become, okay, if I have a Fuchsian group, does there always exist a locally finite fundamental domain? Right? And if so, is it possible to give some way, at least theoretical, to construct such a fundamental domain? Right? That's going to be the next question after we prove our main theorem. Okay, but so as a preparation, we have this exercise. And what the exercise says is that if you give me a locally finite fundamental domain, then around each point in the hyperbolic plane, there is a compact disk of positive radius with the following properties. So I have my Z node, right? And there exists this disk, this hyperbolic disk, with the property that, well, the local finiteness tells me the number of gammas that make d bar overlap it is finite. So somehow I know that actually it doesn't matter what radius I take, right? But the extra property is that for any gamma that makes d bar overlap, necessarily Z naught is already there. Right? So let me just kind of see quickly this property. So I know that for any radius, for this compact open disk. Okay, I don't want to say finitely many images. Can I say that? Yeah, I think I can say that because of this exercise. Yeah. Okay. Yeah, so I can say that. For this compact disk around Z naught, that compact disk intersects only finitely many gamma images of D bar of the fundamental domain, and so somehow the picture is more or less the following. So somehow, let's say that this is one of those gamma translates of D bar, right? So like this, and then there's another one, and then I don't know, another one, and I don't know, here another one, let's say. And then here you can see, for instance, in this one that I drew here, somehow Z naught does not belong to that image. So somehow this one doesn't satisfy the condition here, which means this disk doesn't satisfy that condition. But I know that the number of these images, the number of all of these images is finite by local finiteness of the fundamental domain. And so something that I can do is I can take around Z naught a sufficiently small radius with the property so that the corresponding disk doesn't intersect any of those images here that do not contain Z naught. So considering the kind of my first compact disk around Z naught was arbitrary, and with that compact disk, I was able to to catch only finitely many gamma images of D bar. And once I have only finitely many gamma images of D bar, I can say, okay, because you only have those finitely many gamma images of D bar that intersect your original compact disk, then you can take a sufficiently small so as to exclude those where Z naught does not belong. And for that sufficiently small, you have, well, you still have the first property, right? And now you have the second property as well. Right? I mean, because otherwise, for this small one, if some, you see, for this small one, if it intersected some gamma image, but without Z naught being there, let's say here, then that point would also be in the big one. You see, and somehow it would be like a contradiction on how small I took the radius. So okay, so this may sound a bit kind of even, yeah, a bit like intricate, but it's going to be like we're going to recur to it quite a few times. So around each point in U, there exists a sufficiently small compact disk with the property that, of course, this number of gammas that make it overlap is finite, but also every time someone makes it overlap is because Z naught itself was already there. Right? So somehow Z naught is in the overlap. Okay, so this exercise. This is going to be we're going to be resorting to it quite a few times. And as I said, the theorem is that this iota bar is a homeomorphism if and only if D is locally finite. And the proof is going to be a bit heavy, kind of unfortunately, Yeah, so yeah.
Do you have an example of a fundamental domain which is not locally finite?
I have. So let me see. Not on the top of my head, but I have like in some notes. So I mean, yeah. So I can, if you let me, I can look it up. Yeah. Yeah, because they become a little bit kind of hard to deal with, but
right, it's hard to visualize.
Yeah, yeah. Yeah, but there are, yeah. Yeah, but maybe on Wednesday I can discuss a little bit. Yeah. Because I don't have it on top of my head right now. Yeah. Okay, so the proof of this is a bit heavy. Yeah. So suppose this iota bar, so this map is a homeomorphism. So remember, this is kind of in the fundamental domain. We glue things following the instructions of gamma, and here this is kind of just the orbit space. Right? And that is suppose that is a homeomorphism, but that the fundamental domain is not locally finite. And I'm kind of after a long road, I'm going to arrive at a contradiction, and the contradiction is that something is going to not belong to certain set, and at the same time it is going to belong to the set. But it's going to be a bit long. Okay. Now, since D is not locally finite, there must exist a compact subset of U with the property that the number of gammas that make D bar overlap the compact subset is infinite. Right? Just kind of that's just negation of local finiteness. Okay, now you see for each element here, for each element in this S, I can pick someone in the corresponding intersection, which means that I can pick someone in D bar whose image under sigma belongs to K. Okay? And that's for each element of gamma. So, sorry, for each element of S. So for each element of S, I can pick an element in D bar with the property that sigma of that is in K. So that I can do, and now the point is that I may, you see, the axiom of choice. I mean, because kind of again, for each element of S, I know there is, but how do I know that I can pick all of them at once? So for that, I say, okay, so let's just believe the axiom of choice. Okay, and now what I have then is a set of points in D bar. And now I claim that this set of points of D bar is infinite. Now, suppose not. Suppose that this set is finite. Right? So what I have is this infinite subset of gamma. So S is infinite subset actually of gamma. And then with what I'm doing is I'm producing a function precisely to the set of z's, right? Say sigma in S. Right? I mean, to each element of S, I associate precisely the corresponding z sigma. And then I claim that this set is infinite. But otherwise, if it were finite, so you see what I would have is a function from an infinite set to a finite set. So there would be someone in this finite set whose preimage would be infinite, of course. Okay, so there would be some zt here with the property that for some that with infinite preimage, so with the property that there is some infinite subset T, the preimage, with the property that for all the elements give you the same element in the set, right? And that I would be able to call ZT because all of them would give me the same, right? So this T is kind of this preimage of that, yeah, and then this would be infinite. Okay. Now, this is, you see, S is a subset of sigma, so T would be also an infinite subset of sigma. Did I say sigma? Of gamma, sorry. S is an infinite subset of gamma, so T would also be an infinite subset of gamma. Yeah, and now I go to consider this other set. I know that T is infinite, so this one would have to be infinite, because otherwise, if it were finite, you see these are already points in the hyperbolic plane. If they were only finitely many, so you see I have ZT, so maybe let me draw it. I have ZT, and then I have all these images on the elements of T. So if there were only finitely many, so let's say tau 1 of ZT, etc., and only finitely many, so tau, I don't know, tau L of ZT, and let's say that this covers already, this is the whole set. And then you see on the other hand, T is infinite, and whenever I apply anything in T to this point, I land in one of these. So if these were finite, there would be infinitely many, there would be one of them for which there would be infinitely many elements in T, taking ZT there. So here there would be like infinitely many, right? And then I would be able to do the following. Go with one element, and then you can come back with infinitely many different, etc. And then what I would obtain is that the stabilizer of ZT would be infinite, in contradiction with the fact that gamma is Fuchsian. So this set has to be infinite. So not only T, but the set of all images of this point on the elements of T has to be infinite. And now, being an infinite subset of K, because you see these ones, the Z's have the property that when I apply the corresponding sigma, I land in K. So these ones, when I apply the corresponding tau, I land in K, right? So these ones, this would be an infinite subset of K, which is compact, right? So my original K. So it has to accumulate in K. But then I notice that all of these belong to a single orbit, the orbit of ZT. So what I obtain is an orbit that accumulates in U. But that's also a contradiction to the fact that gamma is Fuchsian. So what must happen that this set is actually infinite? Right? So okay, so it was a bit, it is intricate, but okay. But so I have this set is infinite, and it's, you see, it's the set of points in D bar. You see, it's kind of in D bar that are mapped to K under the corresponding sigma. So that one is an infinite subset of D bar. Okay. Now, right. So now all of these are in K. I mean, sigma of this is in K, sigma of Z sigma, by how I pick Z sigma. Okay, so now I consider the set of images, and now I consider this set, the set sigma of Z sigma in S, right? Because of the way the Z sigmas was, because of the way the Z sigmas were picked, this is a subset of K. Now, there are two possibilities. Either this set is finite or is infinite. Yeah, of course. I mean, that's obvious, right? But if this set is finite, then since the sigmas in here are form an infinite set, there must be like something that repeats infinitely many times. And otherwise, if this is infinite, it's an infinite subset of K, so it has an accumulation point. In either case, there is some K naught, and some sequence of elements here, with the property that the sequence converges to K naught. And it either converges because if this is finite, I can take some constant sequence, the one that gives me infinitely many repetitions of something, or if it's infinite, I can take K naught to be an accumulation point. But in either case, there is some sequence of this form that that converges to K naught in K, some K naught in K, right? And here I notice that the sequence may perfectly be stationary, like if this set is finite. So I'm not claiming that this set is infinite. And again, the point is the following. Each Z sigma is in D bar. So each Z sigma can be approximated by a sequence of elements of D. And so that's what I do. For each n, I look at Z sigma n from this sequence. I look at the Z sigma n, and I approximate it with something in D. And I approximate it with the corresponding index. You see that is kind of good enough for the corresponding n. That I do, and the point is, in order to be able to I know that for each of these there is a Wn, but in order to be able to pick all the Wn's at once, I may need to apply the axiom of choice. Okay, so I believe the axiom of choice, and then I notice the following. This distance is, you see, I used the triangle inequality. So I use D sigma n Wn K naught is less or equal than D of sigma n Wn Wn what? Wn Wn, yeah, sigma n of Z sigma n plus distance of sigma n Z sigma n K naught. And you see, so I mean, this is just triangle inequality, right? So in between, I have just put this point, and now this one. So well, okay, so if you want this one is less than 1 over n, and this one is equal to the distance without the sigma, because sigma is an isometry, yeah, which is less than 1 over n. So this is less than 1 over n. This one is less than 1 over 2n. And what I obtain is that sigma n of wn also goes to k naught as n goes to infinity. And now what I have gained is that now I'm approximating k naught by sigmas of elements of D and not only elements of D bar. So that's what I have gained up to this point.
2 over n.
I'm sorry?
2 over n.
What over n?
Yes, you are right. Sorry. Yes, sorry. Okay. Yeah, but it's still tense, right? Yeah. Okay. So, okay. Now, this we saw that you see if I take different elements of gamma, the image of D under one intersect the image of D under the other is empty. I mean, because beta inverse of gamma of D intersect D is empty, right? Which follows from the fact that D is contained in a fundamental set. So from this, it follows that for different elements of gamma, this is empty. Okay. Now, on the other hand, around this point k naught, you see, it intersects all sigma n's of D for all n's sufficiently large, right? I mean, this is not formally written here. I mean, if you give me any open set around k naught, any open set, doesn't matter how small, that open set will end up kind of swallowing all of this, right? Because this tends to k naught. So that means that open set, no matter how small, is going to intersect all of these for sufficiently large n. All of them. Right? So no matter how small you take that open set. But so that means that for every gamma here and here and there, I would say, for any gamma, k naught is not going to be in gamma of D, because if k naught were in gamma of D for some gamma, you see, gamma of D would be an open set containing k naught, and this gamma of D doesn't intersect any other, let's say, eta of D, or any other beta of D. So I would have this open set without this property. Is it clear, or is it too intricate? Okay, so I claim, okay, up to this point, do you agree that for every open set around k naught, that open set ends up intersecting all of these for sufficiently large? Yeah, like from some point on, you give me any open set around k naught, and from some point on, it intersects all of this. Why? Because the WNs are in D and I have this property. Right? Okay. No matter which open set you give me. Now I claim that because of that, for any gamma in D, k naught is not in gamma of D. And this is no contradiction, because I know that D is contained in some fundamental set. But I've never claimed that D is a fundamental set. So it may be that some orbits do not have representatives in D. So it's perfectly reasonable to expect that there will be that there will be points not covered by the images of D under arbitrary gammas. Okay, so somehow, first of all, this is really not a contradiction to D being a fundamental domain. Now, second, if I claim that for every gamma, K naught does not belong to this image. If it were not true, it would belong to one of them. It would belong to one of them, which would be open because D is open and gamma is a homeomorphism. So this would be an open set containing K naught. And being an open set containing K naught, it eventually intersects all of this. And all the sigma, all of these are different. Yeah, all of these are different. But then that contradicts this property. That for beta different from gamma, this is empty. Because it would actually intersect, like infinitely many. So indeed, K naught is isn't in gamma of D for no matter which gamma you give me. Okay, but you see that means already that you see, since the WNs are all in D, that's how I pick them. The WNs are all in D, and K naught is never in gamma of D, never. So K naught is never in the gamma orbits of the points of C. You see, the points in C belong to D. And so all of them belong to D, right? So K naught cannot be gamma of any of these for any gamma, because otherwise it would be in some gamma of D. Okay, so K naught is not in the gamma orbit of any of the points in C, and that implies that when I project it, the projection is not in P of C, because belonging to that projection would mean that K naught is in the orbit of some element of C by the definition of the projection. The projection P from H, or U if you want, to H modulo gamma. Okay, so with some effort, what I arrive is at some point which does not belong to P of C. Okay, and now I'm going to start the road to show that it has to belong to P of C, and this will be my contradiction. Now, this one cannot accumulate in the hyperbolic plane. Why? Well, suppose this one accumulates in the hyperbolic plane so that I can extract a sequence. Yeah, like actually a converging subsequence. This is written already like a sequence, converging to a point in U, right? And then what I can see is that if you give me any epsilon, there is some index, so that beyond that index, I have you see here, this I can make less than epsilon. But when I make this less than epsilon, I can just apply sigma n inverse, right? And so I can make this one less than epsilon on the one hand, and on the other, this itself I could make less than epsilon. Well, okay, epsilon halves, and then you see I would arrive at this is less than epsilon halves, this is less than epsilon halves. Triangle inequality tells me the distance from this to this is less than epsilon, because here I can put this in this intermediate point. And so what I would obtain is that the sequence of this sigma and j's inverse of K naught would converge to W. But then you see all of these would belong to a single orbit, the orbit of K naught. Again, contradiction to the fact that gamma is Fuchsian. So C cannot accumulate in U, this C. Right? So it cannot accumulate. So if it doesn't accumulate, it has to be closed. If it were not closed, there would be some accumulation point not belonging to it. But then there would be an accumulation point. Okay, so it's closed. And now, on the other hand, you see C consists of all these Wn's, so it's in particular a subset of D. And different points in D are never gamma in the same gamma orbit. They are never gamma congruent. So that means that in this let me go back here. So that means that here the points in D, there's no collapse in going here. In other words, pi inverse of pi of C is C, because there are no collapses, because the points in C belong to D. So they are never in the same gamma orbit. So when I go and I come back, yeah, okay, no, sorry, and this is actually because of something stronger. That's because of these three. Yeah, when I take someone in D, and I project it, and then I come back, I ask about the points in D bar that are gamma congruent to that point, but there aren't. Yeah, so that's the real reason. Okay. Okay, so I have this, right? But so you see here, I'm giving it the identification topology. So the closed sets are precisely those whose inverse image under pi is closed. But this one is closed. So pi of C is closed. So it's closed here. So pi of C. So C is in containing D, and in particular in D bar. Then I have pi of C here, which I just argued is closed in here. And remember, I assumed that iota bar was a homeomorphism. What I assumed was that D was not locally finite. But I did assume that I bar is a homeomorphism. So iota bar of this thing is closed here. Okay, and can also, and actually, because of the commutativity, it can be computed as P of C, P of iota of C. Okay, so P of C is P of iota of C. It's the iota bar of pi of C, and iota is a homeomorphism. So P of C is closed here, right? And now notice I have this. K naught is the limit of this sequence. P is continuous. So I have this is the limit of the P's, of P of those. But sigma n of Wn, P of sigma n of Wn is P of Wn, because sigma n is in the same orbit as Wn. Yeah, and so yeah, so this limit, and this limit is in P of C. Right, because all of these are all the P's of Wn's are in P of C. So this limit, somehow this limit exists. It has to be equal to this, and it has to be in P of C, because P of C is closed. P of C is closed. And so P of K naught is in P of C, but we already saw that it cannot be. Contradiction. What must be wrong? Well, something has to be wrong, and what it turns out to be wrong is that that our assumption of not being locally finite, that has to be wrong. So D has to be locally finite, and that is just one direction. So let's try to see the other direction. The other direction is a bit less cumbersome. Okay. Suppose D is locally finite, and take any open. I mean, I want to see that this is a homeomorphism, right? What I already know is that it is continuous and bijective. So I only need to know that it sends open sets to open sets. So I take an open set and I want to see that its image is open. So I take an open set, an open subset of the domain, right, of iota, an open subset of the domain of iota bar. Right, and now I think of this subset like so let me think. Yeah, no, sorry, I lift it, right? So I lift it, and what I know is that pi inverse of A is open in D bar, but being open in D bar, because D bar has the relative topology, means being the intersection of some open set of the big space, the big underlying space, with the set itself, right? So A is open here, hence pi inverse of A is open in D bar, hence it can be expressed as D bar intersects some open set of the big space. Right, and of course, with because of surjectivity, when I apply pi to the inverse image, I hit everything. Right? Not only part of A, right? So in general, pi of pi inverse of A is contained in A, but surjectivity means that I hit everything. Okay. And now I take so okay, so now yes, and now I claim that that the union of all the gamma translates of this set, that is this one, the union of all those gamma translates, is open in the hyperbolic plane. Okay, so to prove that, take any element of gamma, right, any element here, and any point in the corresponding set of in this union, right? And then somehow we want to produce some open disk around it, completely contained here. Right? Okay, now set W naught to be gamma inverse of this, right? So that it kind of we transport Z naught back to D bar intersect B, and then because of this disk that I mentioned before, that there exists some sufficiently small radius with the property that you see that with the property that, well, this set is finite, and this is by local finiteness, but also that for every element of gamma that makes D bar overlap this compact disk, it makes it overlap because the center was already there. And so this is this exercise that I mentioned here. Here, this one. Okay, so there exists such compact disk, and what I notice is that you see, somehow what I know is that if I pick any point in this compact disk, if I pick any point, that any point belongs to the image of D bar under some element of gamma, because the translates of D bar cover the whole hyperbolic plane, because D bar contains a fundamental set. So if I pick any element here, that element is in let's say eta of d bar for some eta in gamma, right? And then that point, then you see that point, that eta would make this non-empty because I would be picking precisely that point in the intersection. So that eta would belong to S, and so W naught belongs to that eta of d bar. But my point is that that eta is already taken into account, and so what I see, since eta is one of these, what I conclude is that the point that you gave me was in this union already. Okay. Right? I mean, yeah, let's say this is really because in S I'm already taking into account all etas that make this one overlap the image of d bar. So if I take a point, I know that it's in the image of d bar under something, but that something then makes this overlap, so it's already considered. So I have this. Okay. Now let's number the elements of S, and of course starting with the identity, right? And then you see for each of these nus, I have W naught in the corresponding nu of d bar. So when I apply nu inverse to W naught, I always land in d bar. So all of these are in d bar. And being in d bar, it makes sense to apply pi, because pi, you see, pi by definition, it's only defined in d bar. But so what I'm doing here is that it makes sense to apply pi to each of these. Okay, and then, well, actually, yeah, so there's something else that I may not need, but okay, now W naught, let me see. Okay, I ran out of time. Let me just leave it there and start from there on Wednesday. Maybe, okay, let's do this. Let me start over from here on Wednesday. Yeah, because I'm out of time, and I don't want to go over. Maybe if I keep going, I will just keep going for more than half an hour. So, yeah. So I think it's just better to just stop. And okay, see you on Wednesday.